I want to thank the organizers for the invitation. It's very nice to be here. I want to start with, this is going to be a low-tech talk. So I'm actually just going to use the chalkboard. Although the techniques that I will quote, I will quote high-power techniques. But I want to start with a number of acknowledgments. First of all, this is joint work with David Borthwick. And I want to acknowledge the many conversations on this subject with Maciej Swirsky, who made available to us an early preprint of a paper that I think we'll hear something about, the paper by Denker, work of Denker, Schottland, and Swirsky. And I will refer to this as DSZ. Okay. And I also want to acknowledge fruitful email exchange with Nick Trefethen, who also make available to us a certain one of his papers, Trefethen and Chapman. So I will begin with the following observation. So suppose you take an operator T on a Hilbert space, and suppose you have a complex number lambda and a positive epsilon, then it is elementary that the following are equivalent. Number one, that the norm of the resolvent at lambda is greater than 1 over epsilon. 2, that the infimum over non-zero vectors of the norm of T minus lambda acting on psi divided by norm psi be less than or equal to epsilon. And 3, that there exists another operator B, H to H, such that the norm of B be less than or equal to epsilon, and that lambda is in the spectrum of T plus B. And so these two things are equivalent. This is elementary. And so the notion of pseudospectrum is, well, to say that if these things happen, we say that that lambda is in the epsilon pseudospectrum of the operator T. And this notion turns out to be a very important notion in the case that will concern us here when T is non-self-adjoint. And I'm new to the subject, but I know that this pseudospectra, notion of pseudospectra is of interest in applications, numerical analysis. And I can see why, because you see, you're doing numerics. You don't know if epsilon is, if you have a very small epsilon, you don't know whether epsilon is 0 or just very small. So that's clearly an interesting concept. And now there's a very beautiful phenomenon that takes place. So the interesting phenomenon is could be good or bad. I think you can view it from both sides. Is that there are many cases. In many cases, lambda may be in the. Let me just write spec epsilon the epsilon pseudospectrum of T for epsilon very small, very small, and yet the distance from lambda to the true spectrum large. And of course, here, I need to just put quote marks. This is a phenomenon that seems to be very robust and of interest. And so let me give you some examples. Being high-tech, I will try to draw them. Low-tech. The simplest example probably is a matrix T, which is simply, it's an nilpotent matrix that has the number, say, alpha on the upper. And it's an n by n matrix. And then what happens here, if you look over at the lambda plane, then if you look at the circle of radius absolute value of alpha, the norm of the resolvent here inside this disk, the norm of the resolvent is enormous, is exponentially large, so order of e to the an, or a. It's enormous in terms of the size of the matrix. And yet, it is not the case outside here. So here, the resolvent, let me just write in English, norm of the resolvent is, I think it's O of 1. Now, this, you might think this is a degenerate case. This is a nilpotent matrix, so the spectrum is just the origin. And you might think, well, the nilpotent matrices do very weird things. But there are plenty of semi-simple examples. And I don't want to take the time to draw the actual formulas, but I will mention two pictures that I will come back to later. So I claim there is a matrix. So I should put an n in here, which is going to be the 1 over Planck's constant. I claim that there is a matrix. I can tell you what it is conceptually, where the region of interest, where this kind of phenomenon occurs, is an ellipse. So this is the kind of phenomenon that I'm going to be talking about. And yet, this is a semi-simple example where the spectrum is evenly spaced among the foci, the segment joining the foci of the ellipse. This example is you take for the following matrix, you take an element sigma, well, some appropriate. Actually, for any semi-simple sigma in little SL2C, and take the nth representation, of the group big SL2C in the standard realization of polynomials of degree less than or equal to n, with a standard norm, and you get this kind of picture. So you have inside the ellipse, you'll have a very large, in terms of n, a very large norm of the resolvent, even if you are a distance O of 1 away from the true spectrum. So this is an interesting phenomenon. And things can be quite complicated. So I have another example that where instead of having a nice line segment here, we have, it's kind of like a double Y. This is an operator in the enveloping algebra of little SL2C. So the spectrum will accumulate very nicely. I mean, I cannot prove this, by the way. I cannot prove this where the spectrum is. So one of my open questions is, where is the spectrum? We'll talk where is the pseudospectrum about, where is the pseudospectrum, but then where is the spectrum? It's something that I don't know how to answer. And then the relevant region is inside the interior of a lemniscate. And again, the resolvent is huge inside in terms of n, and even though you might be away from the true spectrum. So this is the kind of phenomenon. Now, what is a semi-classical setting? Well, obviously, the semi-classical setting, which I've already alluded to before, is to ask the question, well, relate epsilon and h bar in a semi-classical operator. There's some work that I want to mention. There's some work for Schrödinger operators, for non-self-adjoint Schrödinger operators. Yeah, so I should say, just before I abandon the general phenomenon, so that means you see that what I'm claiming is that in all these examples, you can construct extremely good quasimodes that are far from being a mode. And the reason is that the eigenfunctions are highly non-orthogonal. So the usual proof that if you have a quasimode, you're near a mode breaks down completely because it uses the orthogonality of the eigenfunctions. So for non-self adjoint Schrödinger operators, there are some results by Davies and independently by Redpath that I know about. Then DSZ is for the H-bar pseudo-differential operators. There are many results that I believe Niels might. Are you going to talk about that? Maybe you'll talk about these results. Yeah. Okay. So, but our setting is the Toeplitz setting. So I should. Oh yeah. And the paper of Trefethen and Chapman. Trefethen and Chapman, I want to mention. They work with Toeplitz operators, Berezin-Toeplitz operators, on the torus. I'll remind what this is. And they prove this kind of phenomenon with an exponentially small error term, but for non-smooth symbols. And I'd like to understand how we can do that because our symbols are smooth. So let me remind you of the setting. Okay. Let me remind you then, I will start with our setting, which are the Berezin-Toeplitz. So the setting is the following. We have X, I'm just going to be talking about a Kähler manifold. And already the cases of the torus that I've alluded to, these are a few of the many examples, or the complex projective space are of interest, and which is so we have a Kähler manifold which is quantized with a quantum line bundle, a quantum line bundle. So we have a holomorphic Hermitian line bundle with and the connection has the property that the curvature is up to some constant, the symplectic form, the Kähler form of X. So my examples are with in the compact setting. It's a compact Kähler manifold. Then the quantization of the manifold is by the Hilbert spaces of holomorphic sections. The Hilbert space of the tensor powers. Here, n has the interpretation of 1 over h bar. And the dimension of Hn by the Riemann-Roch theorem is a polynomial which is of the order of n to the 1/2 the dimension of x. And so Berezin-Toeplitz operators. So these are finite dimensional spaces, and they are as I said, it was really a surprise to find out that the paper of Trefethen and Chapman, who are numerical analysts, contains examples that are these Berezin-Toeplitz operators. So let me give you the simplest definition is that we consider the projector from the L2 sections of the nth tensor power into the holomorphic part, the orthogonal projection with respect to the standard Hilbert space structure, the Hilbert space structure of this. And then we take a function of x and n. So x, little x is a variable on the manifold which has an asymptotic expansion of this sort. And then we define the Berezin-Toeplitz operator with full symbol F, dot comma n, right, is obtained by the Toeplitz recipe it's an operator. Actually, it's a little bit misleading perhaps to talk about the operator, but because I really would like to think of a sequence. It's really going to be a sequence of operators. This is the simplest way to say it. It depends on h bar, of course. And Tn is an operator on Hn. So the Hilbert space also depends on h bar in a non-trivial way. And the recipe simply is that you multiply by f dot n, and then you project this way. And so I won't go into the details, but let me remind you that there is a whole symbol calculus for these things, symbolic calculus. And so in particular, of course, f is the principal symbol, leading order term there. F of x is the principal symbol. Symbolic calculus, and there are trace estimates. I won't have time to recall these things. I think many of you know them. So these are the operators that we will be working with, and so in particular the f here. I didn't say this, but f and fj are smooth functions, complex valued functions on the manifold. I want to recall one more thing that I need to state the results, and that's the notion of micro support in this setting. So let's consider now a sequence psi, a sequence of vectors psi n in Hn. And let's assume that it's a reasonable sequence, meaning, say, that the norms of these sequences of the elements in the sequence are bounded, or they're polynomial in n. Let's assume it's a reasonable sequence. So let's assume that the norm of psi n, and of course by this I mean the norm in Hn, is polynomial for some fixed p. So it's a reasonable sequence, and then we say that the micro support of the sequence is the complement of the following set, of the set of points such that they have a neighborhood such that the norm of the sup norm over the neighborhood is O of n to the minus infinity. So this is the norm as a section. This is the absolute values that appear here is the Hermitian structure on L to the tensor power n. So it's I don't know, right. So perhaps I should say that, even though it's not a compact example in Bargmann space, just to make so when x is c to some power n, then the norm of c of x in the norm sense, which is the one I mean there, is the ordinary absolute value times e to the minus norm x squared over n over 2. This is the ordinary. So yeah, I'm just making this remark for people who have seen Bargman space. I mean to put in the weight there. Okay, so that's the setting. And in particular, of course, these kinds of examples include the representation theory of compact Lie groups. So I just want to make clear that this is actually how things started. One of the ways in which these things started is that you take G, say, a unitary group, and then you take X to be a coadjoint orbit, an integral coadjoint orbit or integral coadjoint orbit. And I just want to point out that so then the Hn become representations, are irreducible representations of G, and the infinitesimal representations of the complexification group are Berezin-Toeplitz operators with linear symbols. So I just want to point out that we have this rich structure as an example, but of course this is more general. All right, so let me tell you what the results are. I have until 1:45, I believe, right? Maybe a little shorter, because it's getting late. Okay, so the results are as follows. Theorem 1. So let the sequence T. Oh, I didn't call it. I probably called it something wrong. No? I didn't call it anything. Tn. No, I did. Yeah. Let Tn be a Berezin-Toeplitz operator. So we have the following situation. First of all, so let's assume that we have a point x naught on the manifold is such that the Poisson bracket of the real and the imaginary parts of the principal symbol at x naught are negative. Then there exists a sequence of states such that two things happen. So they are very good quasimodes. Yeah, and then the value, the quasi-eigenvalue is the value of the symbol at that point. Now, how good are they? Well, the estimate is n to the minus infinity. One would like to have an exponential error term there, and I don't think I'll have time, but we're working on that. And furthermore, that the micro support of the sequence is the point in question. Now, I can tell you right away that the reason this condition here appears is really in the end will be it is Hormander's solvability condition. In the end, that's what it is. And Maciek was the first one to make the connection between this type of condition and a pseudospectrum. Trefethen and Chapman have a condition that is equivalent to that, but they only assume differentiability at the one point, x naught. Now, what happens if you have the wrong sign? Then you have sort of hypoellipticity. So assume the Poisson bracket at x naught has the wrong sign, or the opposite sign. then, and suppose that you have a sequence that is a good Quasimode. Any sequence, if it exists, satisfying estimate star, is has micro support away from the point x0. So if such a thing exists, is because it's for some reason that has nothing to do with x0. So that's the first theorem. And I will tell you more about the proof in a moment, because the proof I have to introduce a certain amount of machinery to talk, even say a few words about the proof. I would like to not do that before stating the other results. So let me, but I was going to say something else. Well, I don't remember what it is. Anyway, the second theorem. And this is a theorem where we really follow DSZ. Is the following. So we want to take a point lambda in the boundary. This is the boundary of the image of the principal symbol. Okay. Now, for any multi-index I, let's and for any x, let's define well, first let's define the repeated Poisson bracket of the real and imaginary part. So let me write f to be f1 plus I times f2, real and imaginary parts. So let's define f sub index I to be the repeated Poisson bracket. So these are the Hamilton vector fields. You have a choice for each term whether you take the real or the imaginary part. And let's define k of x to be the maximum of the integers j such that f sub I at x is 0 for all I with length less than or equal to j. Okay, so you have a certain number of vanishings of the Poisson bracket at the point x. And let's assume, so I guess these are notations here. The assumptions are one, is that for every point in the pre-image of lambda, the differential of f at that point is not 0. And two, that the number k, which is defined to be the maximum over the pre-image points of the k of x, is finite. Then Schosten and Zworsky show in their paper that one can then apply these with these assumptions, the hyperellipticity results of Hormander. And then the conclusion is that you get an estimate. You get an estimate like this. Let me make sure I don't make a mistake, because let me just rewrite it in terms of the inf. So P is Tn. Yeah? Did I make that mistake already? No. So we get something that goes the other way. So, and again, these are our contribution to this theorem is simply to show that these assumptions in the Toeplitz setting allow us to apply the hypotheticity results of Horman. There's one more result that I like. It's a simple result, but I'm fond of it. Yes, this is actually a lambda. That's right. Right. So I mean, there's no reason to expect exponential growth all the time. I mean, it really depends on the simplest example of something like this is you can look at a linear Hamiltonian on a complex linear Hamiltonian on the plane, and then you can do the calculation whether that has 0 in the spectrum or not, and you see right away that you end up with a condition on the Poisson bracket of the real and imaginary parts. So let me just mention one more result, which is, as I said, it's not hard, but I'm fond of it. It's about something else on the numerical range of these operators. So the numerical range of Tn is the set of, if Tn were self-adjoint, we would call this the set of observed values of this observable. And this is known to be a convex set. This is the numerical range of omega n. And then you let omega infinity be the limit of these sets. So that means points that are the set of points that are limits of points lambda n in Wn. Then W infinity is the convex hull of the image of the principal symbol. So in the example where so I should revisit the example before I say anything about the proof. Just the pictures that I drew, maybe just one picture. Maybe I think I probably have space here. So I can tell you a little bit more about the intriguing picture where the spectrum goes like this. And then we have this region, this lemniscatic region there. So in the examples, this example, as in the previous other two that I mentioned, the region of interest here is the image of F. And it turns out that for this particular case, so here F is actually is a function on CP1. This is an example that had I been quicker at making computer pictures, I could have shown you. There is beautiful software to make these plots, and even I could use it. And but anyway, so the function is actually a quadratic function. So you think of this as the Riemann sphere inside R3. This is actually a quadratic function, quadratic plus linear, and right. So if you however want to look at the numerical range of this thing, then you have to take the convex hull of the lemniscate. Okay, so those are the results that I wanted to talk about. Let me now say a little bit about the proof, but given that we're running late and the proof is that it reduces to the previous case somehow. So let me just sketch a little bit. The one thing that I really would like to know, and I don't know, and it's driving me crazy, is how to explain those accumulation points. And it's clear that I cannot I mean, I have some ideas. Maybe toward the end, I want to say something about this. But so some ideas regarding the proof. proofs. Well, so all the analysis is done on the manifold P. So this is a technology that we have used before. You have the unit circle bundle. So this is then the set of vectors with length 1 in the dual. So this is an S1 bundle, S1 fiber bundle. And so the bundle here, so P has a connection form. Alpha, which will appear later on. Now, L2, S1 preserves everything, so P is a contact manifold. It has, and S1 preserves all the structures. And if we decompose L2 of P by the Fourier coefficients, then we have the tautology that L2 PK is, I'm going to write equality, this is a tautology here, as the L2 sections of the kth tensor power of L. And if k is negative, you take the tensor powers of the dual. And so the analysis will be done up on this compact manifold P. So in some sense, so here's something. In some sense, you see the Berezin-Toeplitz running ahead of myself. So let H be the Hardy space. Of P. So P is the boundary of the disk bundle, which is pseudo-convex because X is symplectic. The curvature is symplectic. So it's actually a Kähler form. So you have positivity, and and if you now decompose H into its Fourier components, then you find out that you only get non-negative ones by a vanishing theorem, and Hn is the same as the holomorphic sections of the tensor power. And the projector then from L2 of P into H, which is the Zygo projector, is actually, by the identifications above, is simply the direct sum of the projectors pi n that we saw before in the definition of a Berezin-Toeplitz operator. So, in fact, the Berezin-Toeplitz, you can think of it, the Berezin-Toeplitz operator, as the direct sum of all the Tn's that I was talking about before. You have the Tn's that form a certain, you have a big operator on the Hardy space that is block diagonal. The blocks are increasing in size, and each block representing the Hn part. So you have this huge operator. And I believe, I haven't proved this, it occurred to me on the plane that if we were to look, so what is a huge, so the huge operator is of the form pi q pi. I claim that one can choose a pseudo-differential operator q so that the direct sum of the Tn's, now that I've added up all the Hardy spaces, all the spaces of holomorphic sections to make the Hardy space, I can add up the operators, and I claim that it looks like this, where Q is a pseudo-differential operator on the principal bundle. These are results of Boutet de Monvel and Guillemin, and there's a very nice description of this theory that written up by Laurent Charles recently, and it's a very readable exposition. So, but what I was going to say is that if we now look at the spectrum of this, the actual spectrum of that now infinite-dimensional Hilbert space, that I bet it is the image, and what is happening is that as we take the pieces, that we recover this phenomenon of existence of quasimodes. So, Well, so maybe I'll just say one word about Theorem 1. Theorem 1 is on the existence of these very good quasimodes under certain conditions. So the first part of Theorem 1 so let me remind you that's the existence of very good quasimodes, pseudomodes, under the Poisson bracket condition, the sign of the Poisson bracket. So we actually construct, we define a space of distributions which are, we call them polarized Hermite distributions. So I don't want to go into the details. It's long and it's late. Let me just do the simplest description. So the simplest description is when the dimension of X is 2. So we have a surface, and so we define a space of these distributions that, under this trick of decomposing by Fourier components, becomes a sequence. So we define spaces of sequences. With micro support, the one point that we are looking at, and we have a symbolic calculus associated with this. All I want to mention is that the nature of the symbol of one of these polarized Hermite states is a symplectic spinner. Well, let me just summarize by saying that it's a smooth vector in the metaplectic representation of the tangent space to the manifold at that point. So essentially what's happening, and I really wish we had a very concrete description of this. We're using the symplectic spinner machinery, which is heavy, so this is the high-tech part of the talk. Behind the scenes that we're using the calculus of Hermite distributions. And we should be able to write them down. I can tell you that the squeezed coherent states that we saw last in the previous picture, the standard squeezed coherent states are such are an example of such distributions. And so we want to solve Tn of psi n equals 0. And so we actually can do this symbolically by choosing the symbol appropriately. So you have to solve a transport equation. And the transport equation, let me just tell you what it is. The transport equation is an equation in the metaplectic representation. And it turns out to be an equation of the form, if you think of metaplectic representation as a representation of functions of a variable x, is an equation of this sort. And of course, we have to solve this to all orders. And so I have to be able to solve the inhomogeneous equation, where mu here is in the Schwarz space of functions of the variable x. So this type of symbolic calculus leads to this equation, and you want a solution that is also. So we want a solution that is also in the Schwarz space, and that will depend on the sign of that number. And when you do the calculations, you figure out that the sign of that number is related exactly to the Poisson bracket condition. In higher dimensions, the situation is the geometry is richer. You can actually take the inverse image of lambda is actually a symplectics of manifold, and you can take an isotropics of manifold of that. So these spaces are sort of isotropic states. They are not Lagrangian. They are associated to isotropics of manifolds in the scalar setting, and they have symbols that have a transverse component, which is one of these symplectic spinors. Well, I could say more, but maybe we can stop.
Any questions or comments?